In this lesson, we are going to find the area of a surface of revolution. So in an earlier lesson, we found the volume of solids of revolution and how might we find their surface area. So suppose we have a curve, y equals f of x between some a and some b. So divide it up into little pieces. And we're going to spin those little pieces about the x-axis. Now, the surface area of each piece is going to be approximately 2 pi times the radius times the length of the piece. And what you can think is that if you have a cylinder, the distance around that is the circumference, and then times the little bit of length that that sort of like little cylinder has. Now the radius in this case, that is just going to equal y. And the length, well, that's just finding the length of a curve. That's going to be equal to the square root of 1 plus some, y prime of I squared in your little subinterval. So the surface area in general will be about equal to a sum of all these from I equals 1 to n 2 pi y sub I square root 1 plus y prime of I squared times delta x. And it will exactly equal to a to b 2 pi y square root 1 plus, think about y prime as f prime. And then in for y, you can input the actual curve. So 2 pi f of x square root 1 plus f prime of x squared dx. And if you think kind of like circumference and then length of the piece, I think that you can convince yourself that that must be the surface area formula. And so that is for spinning stuff about the x-axis. And the only funny thing about surface area is that you don't always have to use x's when you spin about the x-axis. So this is one equation for spinning about the x-axis. Another equation that you can use would be c to d 2 pi y, and then here instead of f prime of x you could have f prime of y squared dy. And that kind of comes from the fact that when we derived this little arc length formula in a previous lesson, we pulled out dx, and we could have also pulled out dy if we would have just sort of reversed the relationships. So this will also find stuff about the x-axis, and how you can think about that is that you have to have a distance from there up. In this case, that's y, and y can either be f of x or it can be y. Which one you want depends on if your curve is solved for x or for y. Now, if you rotate about the y-axis, your surface area will be given by integral 2 pi x square root 1 plus f prime of x squared dx. And if you use, and that's because your distance away or your radius is now x, so your circumference is 2 pi x, and the little length can be approximated using the 1 plus f prime of x squared thing. If you choose to use x's in your equation, this should be a and b, but you could have also had an integral from c to d 2 pi x equals, say, some function of y square root 1 plus f prime of y squared dy. So to illustrate that difference, let's sort of set up integrals about, same curve rotated about two different axes. So suppose we're spinning e to the negative x squared about the x-axis. And let's say we're talking about between x equals 0, x equals 1. So 0 to 1 about the x-axis. So surface area will equal 2 pi integral 0 to 1. So distance out will be y square root 1 plus y prime squared dx. And in for y, I'm going to stick e to the negative x squared. If I'm choosing to use x's, I have to have x's there. And then remember that y prime is negative 2x e to the negative x squared. So it'll be 1 plus, squaring that gives us 4x squared e to the negative 2x squared. So there's the setup for surface area about the x-axis. If you wanted to set that up with y's, and if you wanted to leave this thing as y, you would have had to solve this equation for x. And you would have also had to know what the y value was there and there. So I think that probably wouldn't be a spectacular way to proceed. If you're going to spin about the y-axis, so we'll say 0 to 1 again. Say how far away is that? Well, that's x away. So surface area will be into 2 pi x square root 1 plus, we'll say f prime of x squared. If we want to use dx's, we can use 0 and 1. So 2 pi integral 0 to 1x square root 1 plus same thing as before, 4x squared e to the negative 2x squared. So that is the surface area about the x-axis. Notice here we chose not to replace x with any kind of equation, so just leave it as x. So suppose the curve root 4 minus x squared between negative 1 and 1 is rotated about the x-axis. So this is a part of a circle of radius 4, 2. And we're spinning just this part about the x-axis. So the surface area will equal 2 pi integral of y square root 1 plus y prime squared dy. And since we have this solved for y, let's actually just plug y in. So 2 pi, and that will be from negative 1 to 1. Okay, we're going to need to input the derivative of this. So calculus 1, y prime is 1/2, 4 minus x squared to the negative 1/2 times negative 2x, or negative x over square root 4 minus x squared. So that's 1 plus x squared over 4 minus x squared. That's after I squared that whole business. So get a common denominator now. So we'll have 4 minus x squared plus x squared over 4 minus x squared. And that becomes square root of 4 over 4 minus x squared. And those 4 minus x squareds actually cancel, and you end up with 2 pi integral negative 1 to 1 of 2. Something simple. 2 pi times 2x evaluated from negative 1 to 1, which gives us 2 pi times 2 minus negative 2, or 2 pi times 4, or 8 pi. This process could be used to prove that the surface area of a circle is 4 pi r squared. So if you want to do that for fun, it's not actually very hard. You can go ahead and give it a try. So now let's rotate something about the y-axis. So we're going to rotate y equals 1 minus x squared between x equals 0 and x equals 1 about the y-axis. Okay, so here my surface area integral, I'm going to fill in the bounds later, so 2 pi distance out, x, that's the circumference, length 1 plus y prime squared. And because this is already solved for y, I'm going to use x's. Let's just say dx, and we'll say x equals 0, x equals 1. And now then y prime is negative 2x, so y prime squared will be 4x squared. And this integral is one you can solve using a u substitution. U equals 1 plus 4x squared. Du is 8x dx. So an eighth du equals x dx. So we'll have 2 pi over 8 eventually. Now let's change our bounds. The lower bound becomes 1, upper bound becomes 5. And I think we just have u to the 1/2. So pi over 4, the antiderivative of u to the 1/2 is u to the 3/2 times 2/3. So that's going to be, I think, pi over 6, 5 to the 3/2 minus 1, or pi over 6 times 5, square root 5 minus 1. Doesn't work out super nicely, but that is the surface area. And here, let's set one up, but not solve it, because I'm pretty sure the solving involves a trig sub that's just pretty tricky, and that's all we want to do, is just set it up. So the curve y equals cosine x is rotated about the x-axis. So cosine begins at 0, or begins at 1 at 0, and by pi halves, it's at 0. And we're going to spin this about the x-axis. So if we think about the circumference of our little slices, that's the radius. That will be y. So 2 pi integral y square root 1 plus y prime squared dx. So we'll go from 0 to pi halves. Let's input what y is. So 2 pi integral 0 to pi over 2 cosine x square root y prime is negative sine 1 plus negative sine x, the quantity squared. One plus sine squared x dx. Now my guess is from here you can do a u sub plus a trig sub, but it just gets really awful, so let's just leave it at that. That's good enough. The last thing we're going to do is an engineering type question. So a group of engineers is going to build a parabolic satellite dish, and the shape is going to be formed by taking a parabola, ax squared, and rotating it about the y-axis. So that parabola will go through the origin. It's supposed to have a 10-foot diameter. So that's going to be 5 over that way and 5 over that way. and be 2 feet deep at its deepest point. So this will be a depth of 2. That means that this point here is over 5 and up 2. And given that information, we can figure out what that A needs to be. So y equals ax squared. So 2 equals a times 5 squared, and therefore a is 2/25. So our parabola is 2/25 x squared. And so the surface area of this object we'll get when we spin this part of the parabola about the y-axis. So that's the integral 2 pi x square root 1 plus f prime of x squared. Let's use dx. So our x's would range from 0 to 5. And f prime will be 4 over 25x, the quantity squared. And that gives us 2 pi integral 0 to 5x square root 1 plus 16 over 625x squared. And from there, it's going to be a little bit tedious, but I think that you can get it. As in, you can do a u substitution for the 1 plus 16 over 625x squared. And it's not going to be pretty, but it's not going to be awful either. In the end, you get this is approximately equal to 90.012. And since it's an area, it's going to be square feet. So since this is pretty closely related to the arc length stuff, this lesson is pretty short, and that's all we're going to do with this. So just make sure you know the formula and how to set up a whole bunch of problems and solve some of the more basic ones where the resulting integral isn't super tedious.